All right, we're back again. Free fall lab that we want to talk about right now. And so a few things to go over from this. This was kind of dependent on data you got. So that really, I thought, kind of made the difference for some people. One thing, had some pre-lab questions in here, and some of you skipped those, and some of you answered them. So just know in the future, if you skip those, then I will be taking points off. So that's a key thing, really, from a teaching perspective and a learning perspective, that you want to be thinking about it ahead of time. And I had some kids who said the ball would accelerate, but then it would stay a constant velocity. So it helps me to see what you're confused on going into it, and then ideally after we've thought about some things and talked about stuff, then you get a better understanding. So just make sure to pay attention to those. I didn't mark them right or wrong because it was pre-lab stuff. So very rarely did I make a note on there. Then next thing we had the data, and there were a couple things that came up here. I put an example of really good data that a student had, and so I thought they must have done some pretty good work. And what you should look for, and some of you who had bad data, that would be very misleading to you in terms of your understanding. So, um, this data was pretty good in that as the height increased, the time increased. Some people did not have that. If you didn't have that, then that means that your data was very bad. So then it would be misleading. So you have to make sure that you're assessing your own data in terms of the time that it took. Because the higher you drop it from, the more time it's going to take. And there is no way that it would be anything different from that. And then, if you didn't watch the video of how to do these, if you got how to do some of these data columns wrong, then that's something you want to go back and look for. I'll probably put in our next assessment some type of doing data like this, where you had to double the average, and then your acceleration was your change in velocity over time. So you want to make sure that you are able to do that, even if you did it incorrectly in the lab. Then here's some data that was not the best. And you can see this person has like an average time of 12 seconds to fall from 2 meters. So that would be like me holding a ball above my head, and I drop it, and then I count 1,000, 2, 1,000, 3, 1,000, all the way to 12, and then it hits the ground. And that would be amazing, but it's so off that you have to be able to think about what you're doing there. And, I'm not sure like where some of these even came from. Um, and so those are the kind of things that you want to be able to be critical of your own data. And if you get weird data when you're doing an experiment, you should go back and repeat it so that you try to get better data, rather than just go with what you got, because that definitely affected what you did when you made graphs. So the whole idea here is that the acceleration due to gravity is constant. It's a constant acceleration. That means that the velocity or the speed is going to change. So your graph of distance versus time, a lot of kids put a trend line in there. I did not want you to, because the shape of that would be a curve. That's an exponential relationship that exists there. And in our small window of distances, we don't always see that right away. So it's a little misleading, um, for us at the beginning of this. But I didn't want you to put a trend line, and that's why I didn't say include a trend line. So that distance time graph, we just had the points on there. And then our velocity time, we'd have a trend line and the equation. And some kids are doing something like this. So this is a misleading graph. So it should absolutely not look like this. But I do not want an R squared value. The R squared value is not the equation for the line. It has nothing to do with that. So some kids are mistaking this for the slope. And like in this one, it would be negative 4.32 would be the slope. And so, doing that equation, and is pretty easy on Google Sheets. So if you're still hand drawing stuff or using some other program, you kind of want to start upgrading and figuring that out. And as we get longer into the year, that's something that you should be able to do pretty simply. And so anyways, if you had a graph like this, what your job to do as a student is to think, would this make sense? Because if you're answering your lab questions based on wrong data, then it's going to be harder. So you've got to think through that, because you know that the ball doesn't slow down as it falls. There's no way for that to happen in free fall, and there's no way that it would happen if we dropped anything like within 3 or 4 meters, unless it was a piece of paper or something that was greatly affected by air resistance. So if you had a negative slope, then you in your head should think, okay, this isn't what happens. And then you might think about, well, why did I get it like this? And for a lot of you, it was timing errors, because the difference is like anything under 5 meters should take less than a second. So we talked about that in class, but when you look at your times, anything under 5 meters should take a second or less. So like even this one, like this is a little bit misleading, because at 6 meters, it should take over a second. So I'm not sure where this person got that, but we would have a little bit of timing error for sure in how we do it. So, think about your graphs, and if you have questions about those, you can ask me. And then we had the data that I gave you in class about dropping these different balls off the balcony at the high school. And I was really kind of confused by the way some of you answered the lab questions that followed. So, the part 2 stuff only was for this last set of questions. So like, where was the ball's velocity the fastest? Some people said golf ball. So, which was such an abstract answer to me, because I didn't really understand it, and it told me you just didn't understand the question. But when we're looking at an object that falls, where is its velocity the fastest? Just before it hits the ground. So it speeds up the whole time, and just before it hits the ground, it's going the fastest. So, I thought that was a pretty simple one. What kind of relationship does the distance and time graph show for an object in free fall? So this, we already knew this from previous labs, but this is an exponential relationship. So as time goes on, the object is moving faster, meaning it's covering more distance. So that's that shape of the graph that starts to increase up. And so people gave me different answers for this, that I think they just weren't thinking about the graph, or they were just interpreting it like the word relationship, what that means. So and when we talk math stuff, we're talking, things can have an inverse relationship. They can be exponential. They can be direct, those kinds of things. And then here, what does the slope of a velocity time graph show? So this is really just a one-word answer that we should know. And this is acceleration. And so the slope of a velocity time graph gives us acceleration, because the change in y is the change in velocity over change in x over time. So change in velocity over time. And then the value for slope. So, and then I want you to say what that means you found, including the units. So even though this graph is misleading, it still has a slope here of negative 4.32. So I would look at that from what I did on my graphs, and I would say, well, this is negative 4.32 was my value for slope. This is the acceleration due to gravity. So you found that because you just told me up here that acceleration was the slope. So the slope is acceleration due to gravity in meters per second. So that's the units. And so ideally, we would have found that this was 10. Some of you, if you have the average velocity, you got it close to 5, you can think about doubling that would get you to 10. But the slope there is the acceleration due to gravity in meters per second squared. Now, why would this lab data be similar to the one from lab 3? So lab 3, we rolled the ball down the ramp. It accelerated. That was our constant acceleration lab. So why should this be similar? Why would the distance time graph be exponential? Why would the velocity time graph be linear with a positive slope? And this is simply because both labs were looking at an object that had constant acceleration. So they didn't have constant velocities because they were accelerating. So one is accelerating due to gravity. The other one is accelerating because of gravity, but it's not in free fall, so it's going down the ramp. Both of those had constant acceleration. And you should be able to think about those two labs as similar concepts, but just different situations. So last thing here, we looked at part 2 data and what was true about the time for each ball to hit the ground. So we had talked about this in class, and I look at this and, these are all off by, 100th of a second. So this is me dropping these off. So some people start talking about distance and stuff like that. All these distances are the exact same. So I'm not sure where that came from, but what was true about the time, they were all the same. And that 100th of a second is insignificant in the way we collected this data. And then what that means about the acceleration of different objects in free fall is that all objects accelerate at the same rate, regardless of size or mass, anything about them. So in free fall, remember, we're neglecting air resistance, but some kids, it was only a handful, but we're like, oh, big, heavier things will fall faster. And that I've usually commented on there, no, because that is the most wrong thing you could think about in this. And so you want to really have an understanding that all objects will accelerate at the same rate, and that's 10 meters per second squared, regardless of their size and mass. So, and then I put this to think about, does the Earth pull everything equally? And I do want you to be thinking about that because we'll get to it fairly soon. And so we know things accelerate equally. So does that mean that they're being pulled equally? So kind of chomp on that one a little bit. And so let me know if you have questions about this lab at all, and we will see you in class.